All right, are we ready to get started? Okay, let's do this. Share screen. Okay, welcome back everyone to the What's a Microcontroller with Python and the Microbit version 2.0. This is workshop day 2 on Wednesday, November 19th. So yesterday we went over introductions and talked about a little bit about code. And then also we did some setup and testing with our breadboard kit. One thing we did not get to was the first circuit. We skipped over that and built a larger circuit that we'll play with today. So one thing I'm going to do is just talk briefly about the first circuit, because there are some important things that students will be going through here before they start experimenting with the circuits that we are experimenting with here today. I'm also going to mix in a measurements chapter as we go through today. So today we'll be playing with the lights and the push buttons and talking about some of the different concepts that accompany that. So this was the homework. I'll go ahead and paste in a direct link to this slide just in case anybody needs to try to build this post haste during the workshop. Okay, so that's a direct link to the homework slide. And then there is a schematic that accompanies it. And I'm not going to go into detail on this right now because we haven't talked about how the students are introduced to schematics or about any of the parts on this schematic, but it is accompanying the wiring diagram. And for those of you who already know a little bit about circuits, it can provide some reality checks if you're not sure about a connection on the breadboard. All right. Oh, by the way, so how did the homework go? Are we mostly good with having those circuits built up? I know some of you had some time crunch things. Oh, looking good, Sarah. Anybody else? I did mine. There we go. All right. Okay, so what did we skip? We skipped actually quite a bit before building that circuit. The main thing I wanted to talk with you about is the end of the first chapter. And then there's actually an entire second chapter between this and building and making the light blink. So this first chapter right here, or I'm sorry, this is not the chapter. This is the last activity of the first chapter. So this is where we set up power for our circuit. So this is where we left off at the end of Monday. And so picking back up here, we now have the students will have a light emitting diode circuit, but instead of connecting it directly to the microbit as we did in our circuit right here. So all these resistors are coming over to rows that share pins with the edge adapter. And so we can write programs to make the microbit send high and low signals to turn the LED lights on and off, and read high and low signals sent by the push buttons, depending on whether you're pressing them or not. And the microbit can then, either get the information or send the information according to a script that you write. But before that, we're going to take just one light and connect it to power. So that's what's going to happen here. And along the way, what we're trying to do is introduce the concept of, okay, we have a nice little drawing of how this circuit is built, but we also want a schematic, or we also want to show students, hey, there is a notation called schematic notation that is used to represent how this circuit is built. And in the real world, if you get a job in electricity or electronics, or even auto mechanics, et cetera, that there's so many different places where schematics are used without a nice little wiring diagram like this, that that it's kind of an important skill to maybe get a leg up on. By the way, pro tip, if you're on the Learn site, which I should paste into you at 1:06 p.m. Okay, so here is the page I'm on right now, or pardon me, actually, I'll paste in the page I started at. All right, there we go. And that's just for reference. We won't be doing anything on here, and please especially do not unbuild any of the circuits that you built to make it match this. You've got what you need for today. All right, so you can hit the left and right arrows on your keyboard to go to the next and previous pages. So instead of clicking this little next page, I can hit the right arrow on my keyboard and get there too. So we try to make it really clear, especially early on, what students need to gather in order to build their circuits. Now, in later activities, it'll just say resistor 1 kilo ohm, and it'll list the colors for reference. But here early on, when it's the first time they've handled a part, we think it's important to make sure that they can see, okay, well, this is the part's name. This is what the part looks like. It has these little color bands that can help you identify it, which will be introduced very shortly. And then it has a schematic symbol. And so we're trying to get all that visually in front of everyone as they go through. And so they go and they gather these parts. And then again, this is what we left off at the end of yesterday. Going to the next page. Again, we're really trying to emphasize, am I not sharing? No, I am sharing. Good. Can everybody see my screen? Okay, excellent. Thumbs up. Thank you. So one of the things that we're trying to emphasize as they build their first circuit is that you've got these parts over here, and that as you connect each part to the breadboard, it forms a portion of the schematic. So there's the light, the resistor, and let's see, I'm actually just going to open this in a new tab for the full resolution version, because it's a nice one to run with your students potentially and discuss it with them before they start building it. So we can say, okay, you've got your parts up here, and then you're going to place your first part, which is a jumper wire connected to the battery's negative terminal, or we call it ground in this case. And so here is that connection. I kind of glossed over it, but basically right here, this edge adapter has pins that are connected to the ground and or negative supply end of the USB cable, and also the ground end or negative supply end of a battery if it's connected. And those go to these sockets next to the blue line. And then yesterday, we also talked about how these bus strips are columns of interconnected sockets. And so we have a column of interconnected sockets here, and then a jumper wire that's connecting the blue line on the left to the blue line column in the center, and then another jumper that's going to the blue line column on the right. And then as for power, that comes from this 3V pin right here. And we intentionally do not give any power from this 3V to over here. This, the red column on the far left over here is only receives power when you plug in the battery pack. And so anytime you need battery power, you can connect a jumper wire to one of these sockets. These sockets are where the 3-volt supply from the USB comes in. And if you disconnect USB and have a battery connected, it's where then you will get battery supply here as well. But without the battery, it's purely USB here. And so this jumps over to the center red column, and then we have 3 volts over here on the right column, and voltage is also introduced as the electrical pressure that runs current through a circuit, but I'm getting ahead of myself. So, so here we have starting to build the circuit with first the jumper wire, and that's basically, hey, there's a ground connection. It's not connected to anything yet. Then the next thing we'll do is take that 220 ohm red, brown, gold resistor, or I'm sorry, the next thing we'll do is take the light emitting diode and connect it, and make sure to have the long leg of your light emitting diode on this side. And the tutorials talk about, okay, this is the long leg, and it's called the anode, and then this is called the cathode, and that's how it corresponds to the schematic symbol. And so the nice thing is that as you place the part, the schematic symbol also appears. And then when you plug one end of the resistor in, it's sticking up in the air. And so it's connected to the LED's anode leg here, and then it's sticking up in the air. There's no connection. But when you bend it and connect it into the 3-volt power rail here, then we see the 3.3 volt supply schematic symbol. And after that, we check it very carefully to make sure everything's connected properly. And then you're ready for the next step as a student. And so the next step is to basically plug in power. And when you plug in power with the LED connected thusly, by connecting the USB cable, you want the light to come on. And so that's all the students do here, is they just check to make sure, hey, the light comes on when you connect power, because you've wired it just like that. Then we talk about the parts in detail, and that always follows the main activity. So basically the activity starts out as find the parts, build the circuit, run whatever test you're going to run, and that may involve the script. Then there's a how it works, followed by some more information. And in that more information, I'm gonna come back to that. There's a format that we have for most of the lessons, but I just realized that this one is a little bit of an exception because it's still pretty early on in the tutorials. All right, so anyway, we talk about the individual parts that they worked with, and we talk about how the way they connected the parts on the breadboard corresponds to a schematic. We also talk about those little stripes on the resistor. For anybody who's interested in learning this now and doesn't already know, these color codes correspond. There's a certain list of color codes that correspond to numbers, and those are the first 3 stripes on a 4-band resistor. And then the 4th stripe or color band has a color that tells essentially how accurate you can expect its actual resistance value to be. And resistance is also introduced as, hey, this is the resistance to the flow of current. So if you have current trying to flow through because voltage applies pressure and makes it want to do so, that this part will resist that flow of current, which will prevent the light from getting too bright and then burning out. So these numbers here on the first band, we have basically 2 digits. And in this case, red corresponds with the number 2. So we have 2, 2. And then the 3rd band is basically the number of zeros to add, although a lot of classes say you multiply by times 10 to the x, where x in this case is 1. So times 10. But that's also, just to make it simple, this is the number of zeros you add to the resistance value. So 2, 2, add 1 0, you get 220. and then check the gold band, and that is 5% tolerance. So it's plus or minus 5% as to how accurate you can expect it to be. We also talk about electron flow because in the physical world, electrons are coming from the negative terminal of a battery, but most of the time in electronics documentation and textbooks, you will see current flow as going actually the opposite direction of electron flow. And I've heard stories that this convention was established because Benjamin Franklin did not actually know which direction the electrons were flowing when he did his early work, because they didn't know about electrons necessarily then. Okay. Then the last thing that is done here is that we try putting a larger resistor in just to see the light getting dim. And then we look at that a lot closer in the next chapter. Every chapter also has a review and practice where there's a self-check of the major concepts. There's, since this is the first chapter, it's not exactly like in later chapters, but we have some exercises here for students to do that challenge them to draw in connections on the breadboard. And then here are the solutions to those exercises. And there's a second set that's in the assessment materials that we'll talk about on Friday. Okay, so that's getting caught up to building our first light circuit for blinking, or well, rather, that's getting us caught up to the end of this chapter. Are there any questions or comments before I move on? Okay, good. Feel free to jump in with questions. I don't necessarily see the chat. I'm checking to see if Stephanie is here yet. If I have Stephanie or Aristides. Do I have a co-host of any sort? There she is. Stephanie is here. Okay, good. So Stephanie will be, I think, looking at your chats, and she'll go ahead and let me know if there's a question, but also please feel free to just unmute yourself and say, hey, Andy, I have a question or a comment. All right. So next up, I'm going to skip this for now because I'd like us all to do something and have some fun with the circuits, at least between showing what's contained in the textbook, the online textbook. So here is our first blinking light. And I want to emphasize again, leave all this circuit in place. Do not take anything apart, even though you will see less in some of the circuits that are documented that we'll be working with. So the first one is in LED lights. That's basically the third chapter. And this is just kind of sort of an intro or curiosity getter that is actually featured later in the chapter. And so we talk about, hey, what is an LED light? Why do we have it? And the answer is because there are the little lights on all kinds of different devices that tell us status. And so again, we started with this, a light that just comes on when you plug in power. And then the change that is made is this connection right here is unplugged and then connected to the P14 IO pin on the microbit edge adapter. And so now the schematic and the circuit has changed, and these little red check marks are what guide the students through that. Okay, after building the circuit, there's basically a test script that we use to just make sure that the circuit is working. We always start with the most basic of things like that first. And so here is that script. And we'll take that, I just pasted it into the chat, and we'll take that and go to python.microbit.org, which I'll also paste in. Okay, so everybody go to python.microbit.org and then go ahead and paste in your test script, and please verify that the indentation came with it. So everybody have something like this. All right. Ready to move on? Okay, excellent. Thumbs up and head nods. All right, so the next thing is to make sure that your microbit is connected to your computer with the USB cable. So check your cable. And then after that, hit connect. And the microbit should show here. If it does not show, you may want to unplug and replug your USB cable so that it shows up. And then, but if it does show, simply select it and hit connect. And then here we have our, this is showing us that we're connected. Now, then go ahead and hit the flash button, and that should load it into the microbit. And once the script is in the microbit, your result should resemble this. Let's see, is it visible? I can't see the light blinking very well. Okay, so essentially, this light right here, there we go. We can actually see it blinking now. All right. So that's one light blinking. And then the instructions on this page have the students go through and try some things. Like they're starting with sleep 500, and I don't recommend this one, but we say, all right, try sleep 2500 and ask them to, examine and report the effect, and then change it to sleep 100, which is kind of fun. So we could try that. We could change sleep 500 to sleep 100 and then flash it. And then looking at the LED lights, it should start blinking pretty quickly. Is that what you guys have? Okay, good deal. And then remember to shout out stop if you need me to give you some time. Pardon me, I'm off screen adjusting the size of a window. All right, now I wanted to talk about how to save and save as and other things that have file menu things in, say, Microsoft Word, but not here. There is still a save and a save as. So right now we're saying that the script name is microbit program, but we want to call it LED blink. So what I want you to do is either copy or type in over microbit program, type in LED blink. And then once you've named it, this is important, so heads up everyone, to save it, especially while we are connected, because Flash won't download a file for us. If we're disconnected, this becomes download, and we do get a file that way. But either way, whether or not we're connected, load save always has the option of downloading a project hex. And so I want you all to try that. And then make a note that it should have downloaded an LED blink hex file that's showing in your recent Chrome downloads.
Andy?
Yeah.
Can you screen share that?
Oh, for goodness sakes. I'm sorry about that. Thank you. I will screen share that. Let's see here. Trying to get back to my Zoom menu. Share. Okay, so let's do that again. Load save, download project hex, and then it appears on your Chrome downloads bar here after clicking script name and typing in the name you want to give the script, which happens to correspond with the name that we have in a comment on the top, which is preceded by a hashtag or pound sign. Any more questions before I move on? We've got while true, which is the way to repeat something infinitely. And then this is the way to send a high signal. This is the way to delay. This is the way to send a low signal to turn the LED off. This turn the LED on, another delay. It does that over and over again. And I just got ahead of myself because there's a nice graphic for that coming up. Okay. So since you now, the one thing I meant to do was actually have everybody save this as something else. So LED blink 100, for example, and then we'll save that. And then go back to 500s for the sleep values. And that was the original example that was in the book. So we'll change its name back to LED blink and save that. And so now we should have LED blink 100 and just plain old LED blink. So next thing you can do is if you want to open a file. So we have LED blink, which I'll go ahead and drag and drop into the editor pane. And that's the original. Then we have LED blink 100. And when I drag and drop that in, we'll see that that is the saved version where the value was changed to 100. And all of those are going to be in your downloads, which I have on another screen. And then they don't have to live in your downloads. You can put them anywhere you want, but they start with, that's where they usually get started, as long as, assuming that that's your Chrome browser's default, that your Chrome browser is using the default downloads folder. You can also set that to a different folder inside Chrome settings. And so basically here we have, actually the second time or third time I saved LED blink along with LED blink 100. And so you can take these two and put them in some other folder. Okay, next up is, again, how it works. And this is where that nice little graphic I was talking about lives. And so talking with your students about how this works, we can start out with, okay, here we have while true, and everything below and indented from it will repeat over and over again because it's below and indented from while true. And when it gets to line 6, which is pin 14, write digital 1, what pin 14 does is inside the microbit connects P14, its pin 14, to 3.3 volts for you. So that applies 3.3 volts to this side of the circuit. There is ground or 0 volts on the other side of the circuit. That's electrical pressure, so current flows through the circuit, which has been discussed, and I skipped over a chapter where we talk about all these things that I hope to revisit before the end of the session. And so that pushes the current through the circuit and when that happens, the light comes on. Now, then it sleeps, in this case, for 2,500 milliseconds or 2.5 seconds. And then with the pin 14 write digital 0, what that does is it causes the microbit inside to change the connection that P14 has from 3 volts to ground. Well, if there's ground on one side and then ground on the other side, there's no electrical pressure across the circuit, no current flows through, and so no light comes on. Then it sleeps for 2,500 milliseconds again. And then in the MP4 version of this, to make the while true go, you actually have to rewind and, and go back through it. So that's hopefully a helpful teaching aid to use with the students. And it also shows, it's also a nice graphic, and the explanation that I just gave is also right here. So then after explaining how something works in the how it works session, we usually follow it with a try this. And what the try this has is it has something for the students to change, but it's not something that they can copy and paste. It's a picture of a change that was made. And so it's going to be up to them to change the while true from the previous program up here to for n in range 0, 10. And then they can see that, hey, the light blinked 10 times. And we try to do that in every try this, is to get the students to put their hands on the keyboard and write some code without copying and pasting, so that they start writing the code. The informational part of any given activity follows the try this. And in this case, the subject of this informational part is on-off signals. And in this informational part, we say, okay, a signal goes on and off. Well, because of that, it has some characteristics. And so we talk about the characteristics of a signal that goes on and off. We have frequency, which is how rapidly it turns on and off. We have period, which is basically how long a signal lasts before it repeats itself. So period is how long a signal lasts. And then frequency is how rapidly it repeats. And then there's also one called duty cycle, which is the amount of time the signal spends on relative to the total time of the signal. And after introducing those things about on-off signals, we have a your turn. Now, sometimes, generally speaking, I try to make the your turn something where we challenge the students without an answer, and then the answer is provided in the teacher-only materials that we'll talk about on Friday. But sometimes sometimes when the when the program is maybe kind of a larger leap, then we want it to be, I do just include the solution as a whole and have them type it in. And so that's what's happening here. And this particular one causes the light to blink more quickly, faster, and then slower. And it's kind of neat. And I think I have this available for you. So let's see if on-off signals. Here we go. So you can download this hex file as soon as I paste it in for you. And let's all try that actually. So we want to download, I just pasted in the hex file. I'll download it from here. Okay, so what's going to happen is you're going to come to a Google Drive page that says no preview is available, but there is a download button. So go ahead and download it. And then it should appear on your Chrome downloads. Everybody got that? Okay, I'm not getting all nods yet. Give me some thumbs up when you're ready.
What was the name of the file?
Let's see. Well, I pasted it into the chat. The name of the file is LED variable blink something. Let's see here. LED blink variable rate dot hex. Excellent. Okay, so once you've got that, go back to your Python editor and drag and drop that in. And then flash it. And then when you look at your light, it should go from blinking rapidly to slowly and then rapidly again. All right. Now that is one that we don't make available to the students, only to the teachers. And next up is, okay, so just another look at review and practice. So this is a more typical review and practice where we have, did you get the major concepts of that activity? And then half of the total questions are here for practice and have solutions. And then the other half is in the assessment materials that are available to you that, again, we'll talk about on Friday. Likewise with exercises and projects. So this gives a lot of practice. And then you have, in addition to that, a lot to either assign or include in quizzes or texts. And then here are the answers. And so that's an activity. And so we have, again, we have something informational. I'm sorry. We start with, okay, connect it. And then something involving a script to test it. Then an explanation of how it works. With the how it works in mind, then there's a put your hands on the keyboard or on the circuit, depending on the activity, to extend how it works in some way, followed by something informational. I used to call this the did you know section, but it just seemed to take away from the actual subject. But this extra information then is followed by a your turn, which normally asks the students, hey, with what you just learned, why don't you go ahead and, extend your script or your circuit in some way. And again, in this case, because the extension of the script was maybe a little bit more than a simple step, I went ahead and just include the solved script, and the students are just typing it in. Okay. So we have set brightness. In the interest of time, what the heck? Let's go ahead and just run the code without, because that'll at least be kind of fun. So here is an example program with some LED brightnesses that I'll paste into the chat. You can try it out. This one starts out pretty dim. And so what, I better just do this one more time. So we're gonna take it, me from the page and you from the script. So you might want to save your work. So we have LED. So the name of this is, oh no. So this was a complete script. So it has the name and everything for you. So we don't need to save that. It's already in your downloads. So we can go ahead and paste over it. But just remember that after pasting over it, you'll also want to take the name and paste it over the script name so that you can save your work. And so that you can harp on your students to save their work. And so after flashing this, we're what's going to happen is that pin 14 right analog will rapidly blink the LED so fast that we can't see it, but it will stay on for 128 10/24 of the time. And it blinks at about 50 times a second. And it'll do that for 1 second and then go through and, by the way, that's 1/8 brightness roughly. And then this is 1/4 brightness, 1/2 brightness, and then max brightness. 10/23, 10/24. So let me know when you've got your light cycling through different brightnesses, that yellow light. Good deal, Edward. Thank you, Bob, Nancy, Rich, Ryan. Good job. Okay. Next up is adding a light. Well, we already added the light, but this will make it go more quickly. So when we add a light, we try to, again, isolate everything. So the script and test, well, in this case, the script is just basically making both of the lights turn on. Normally, I'd only make the one light turn on, and I'm not sure why I didn't do that here. But regardless, here's the next script going into the chat.
You have a little question there first.
Okay, thank
Real
you.
world connection. Is this how they do those cool light displays for Christmas?
It's related to it. There are, you know, I think in terms of real world application, yes, you could make a very small Christmas tree on your breadboard, which would be really cool as an application. And then additionally, what we do is challenge the students and say, hey, make a traffic light controller. You've got your red, yellow, and green lights all ready to go in your kit. So the next step is actually a programming only activity where it talks about how to create a list in Python. And this is leading into the next thing, which is a sequence, how to set up a custom sequence for how you want your lights to go on and off. And so we start out with, okay, this is a programming only activity. And I think it's worth having us try this out because I just pasted it in. Okay, so remember, we have LED brightnesses as the script name. You can hit load save and then download project hex. And then you've got a copy. Do that before selecting all, Control A, and pasting in Control V. And then if you want to save this script, remember to change the name and then hit load save and download project hex. And when you run this, nothing's going to happen on your breadboard. The light isn't going to change color or brightness or anything like that. But when you do flash it, after you're done flashing, click Open Serial. And you will see the result of the list. And so the students are challenged to understand it after typing it in. And so the next step is, hey, how does this really work? And I'm in the wrong one. Let's see here. Set brightness, intro to lists. There we go. Okay. So in how it works, we have another step-by-step animated GIF that you can open and go through very slowly. And this one actually has some questions to answer about, it says, hey, look at this carefully and answer some questions. Except for, I'm sorry, I don't see that. I'll have to, where did that go? Okay, I'm thinking about probably one that comes a little later on. Okay, so here we say, okay, C list equals, that C is for color, color list equals green, yellow, and red. And what this is showing right here is that if you want to access those in your code, you say C list of 0, C list of 1, C list of 2. And then index is being set to 0. This is showing that index stores the value 0. Then we're going to the while true. And the first time through, index is 0, because that's what we just set it to. And C list of 0, with the square brackets there, is referring to green. So C list of index when index is 0 is really green. And it's showing that this whole thing now corresponds to green, and that gets copied over and stored by the color variable. And then you can move on and say, okay, well, it's going to print green. And then it will sleep for a second. And then it will take index, which is 0, add 1 to it. And so the result is 1. And then it'll check and say, hey, is index greater than the length of C list? 1, 2, 3. Well, index is 1. The length of C list is 3. So that's not true. So we'll skip all this below it and move back to the top. So here's a little aid for Python scripting and understanding a larger program with indentation and lists, which were just introduced. Are there any questions before I move on? Okay. As always, feel free to
Hey,
jump.
Andy.
Good. Thank you. Somebody jumped in. Good.
Yes, I have a big question.
Okay.
Especially from what you're going through now. When we've always used your product for teaching basics, P-Basic.
Yes.
Our guys already knew electronics from a year in. So we use this to teach programming.
Okay.
So is there enough here? I mean, I see addressing modes popping in here. Is there enough detail here to teach them what's going on in here? And the second part of that question is, I know nothing about Python except from last Sunday when I started this.
Okay.
Is there a good, and maybe somebody else knows this too, is there a good place to get some, self-training on Python?
Yeah, there's okay, let me take those one at a time. All right. So one good resource for getting started, let me think about this. I think I actually glossed over Python even in the I think I even glossed over Python in the training that I referred to. Let's see, where is the best place to get started with Python? I would say, okay. Okay, so the first spot would be at learn.parallax.com. As far as a step-by-step through Python, the writing microbit programs. So I had everybody try out just the first example program in each of the sections as homework. Let's see here. Paste that into the chat. So that's one. The idea is that here is making decisions. So we did this as part of the homework, but there's more decision making here. And more decision making. And Boolean operators to say this and that has to be true. And so it goes deeper than we looked at as part of the homework or part of the quick, here's just barely enough Python programming to get started. So this tutorial that's at the beginning of the What's a Microcontroller and at the beginning of the Cyberbot is a good starting point. Where'd it go? Here we are, writing microbit programs. All right, so another one is from the help menu in the Python editor. There it is. Okay, so you can click help and select documentation. So this also has a step-by-step set of lessons that take you through microbit only things with example programs and explanations as you go. Let me go back to the beginning. Yeah. Okay, so here's the second link in answer to the programming primer question. A third answer to the programming primer question would be the Make It Code It site. That is mentioned right here. So this is what the Make It Code It site looks like. And each one, for example, Beating Heart, has a nice little video introduction, how it works, parts you need. And here's the make code version, which is the make code blocks. And then here's the Python version. And you can go ahead and open that in Python and then run it, then go back to the tutorial. And it has some challenges on how to change or on changing the program to improve it. Let's see here. So I want to give you this link. That's more of a project-based introduction. One final Python primer is at www.parallax.com. I'll just do a quick search for Python. There's a nice little textbook that goes with the microbit. Here it is. Really good question. Thanks for asking. And so here is a link to the printed textbook. For a deep dive into Python, not MicroPython, Python programming by, okay, so there's by John Zell. Okay, thank you for adding that in, Rich. Okay, so that also is in the chat. All right, feel like that's enough? Cool. Great. All righty. Okay, so back to what I wanted to do next was talk about some of the other things we skipped over just real quickly before going. And oh goodness, no, I actually want to make sure I don't skip measure the blinking light with a voltmeter. Okay, so here is, so next we're going to measure the blinking light, first with a voltmeter and then with an oscilloscope to start learning about different ways of displaying frequency measurements that I mentioned in the informational section. So again, don't pull anything off your breadboard. See here, copy link address. Okay, so here is the link. Oh, shoot, I did that out of order. Here is the page. And then here is the link. The link is what you'll want to open in a new tab. Oopsie, no, you don't. I'm sorry. The link is what you want to download. Save link as. So right click and save link as, and it'll go into your downloads, and then it will be ready here. Okay, so once you've downloaded that, go ahead and drag it into your python.microbit.org text editor, and it should look like this. Oh, Corey, thank you for mentioning it. Yeah, I agree. The Cyberscope is really neat, and you can learn and do a lot with it. All right, so we want to make sure that we're connected. I think I disconnected. You guys should still be connected, and then hit flash to load the code into the microbit. Now I'm going to give you a quick under the hood. I'll wait on the under the hood view. After you have flashed it to your microbit, I want you to hit disconnect. And then we're going to go to cyberscope.parallax.com. I'll paste that in. There you go, cyberscope.parallax.com. So you want to be disconnected in the microbit programming software. And then we're going to go to the cyber, and you want to have loaded this into your microbit. After you've done that, we'll go to cyberscope.parallax.com and hit connect. And then if you have more than one serial port like I do, look for the embed serial port and hit connect. And when you do that, it should show you a voltage measurement, which since I went a little bit out of order, is not showing me much of anything, because what we need to do is we need to place those probes on the circuit as shown here. So go ahead and take a look at the circuit in, actually, some of you may just want the page, so I'm pasting the page with the circuit in now. So this is the circuit, and we want to put our probes, we want to put our black alligator clip probe on the far right column next to the blue line. Just pick a socket that's easily accessible. And then we want to put our red probe on P13. And then, of course, the other end of the alligator clips the black one needs to be on P0 on the 3-pin header, and the red one needs to be on P2. P2. .71 volts. That's about right. The microbit does not have a strong driver when it's sending that high signal and the light is on. So 2.71 volts sounds about right to me. Let's see what my Cyberscope. Oh, 2.70. So we're about 1/100 of a volt off from each other. 2.69, yep. It's all in the expected range. Very good. And so what it's showing is that the microbit is applying voltage. Just to freestyle a little bit, I think I'll unplug the resistor end, and we should see without the resistor plugged in, notice that now it's 3.3 volts. So the microbit does its best to keep it at 3.3 volts, but it cannot quite make it when it has a circuit drawing current through it. So it drops to 2.7 volts. And this again is, I even set up the display so that it's like a voltmeter. Questions, comments? Folks are still working on it, I think. Okay, so I'm going to put the circuit back up just to give you, make sure you can get to that. I have 4 reporting measurements all in the same range, but I don't want to move on until everybody's feeling like they're in good shape. Okay, are the materials we were sent already put together as a kit for student use, or would we buy everything separately to do the activities with students? Okay, the answer to that question is that the materials are already put together. And so let's see, which slide is that on? That is on slide 10. So I will go ahead and copy the complete kit and the replenishment parts links. And Stephanie, if you're listening, could you please paste in the all things microbit link?
Sure.
Oh,
I can
thank
do
you.
that.
Yes, and Corey mentioned that Parallax has a classroom kit, and when we get to the all things microbit link,
There we go.
thank you, Stephanie. Okay, so here we go. This is the category microbit link going into the chat. So this has, for example, a 10-pack of the Cyberbot.
Those are 12 packs.
Oh, pardon me, 12-pack. A 12-pack of the Cyberbot, 12-pack of the What's a Microcontroller kit that we're working with here. These classroom packs have some extra bonus parts that the individual kit does not have. The individual kit has everything that's documented in the main textbook. And then there's like a added project section. I will show you that in the Cyberbot. Let's see here. Oh, interesting. Okay, I will show this to you in learn.parallax.com instead. Just as an example, when you have extra parts from a class pack, there's prerequisites for programming, there's main lessons, and then there are projects. And so the parts included in the class pack, like for the Cyberbot, the line follower and the ping ultrasonic distance sensor, these things are added on in the projects. So that those extra parts in the class packs are typically documented in the projects section. Okay. And there are quite a few different flavors of kits available. So here's what's a microcontroller, just the electronics pack. So if students drop some parts, you may want to get a couple of these just to have extra parts on hand to replenish kits. Here's the kit without a microbit for classrooms that already have a whole set of microbits. They can just get the rest of the kit without worrying about doubling up on their microbits. There's microbit only. And then there's the complete kit that has the microbit and the rest of the parts for the what's a microcontroller stuff. Let's see here. So electrical measurements. This is what we skipped to get to our circuit. So we talk about, hey, let's build a circuit and let's measure it. So this we talked about earlier. It's repeated here. But then we're measuring volts. And so this is showing, okay, here is 3 volts. Now, keep in mind that this is not connected to the microbit. This is connected to the main power, which is why 3 volts was what we saw instead of 2.7 volts. So coming back around, there's no volts here because the probes are connected together. Now it's 3.3 volts roughly. And then there's 1.2 volts across the resistor and 2.06 volts across the light emitting diode. So 1.2 plus 2.2 plus 1.26 adds up to 3.26. And that's an important little thing. And we always update the schematic each time they're taking a different measurement. And so that brings us into things like Kirchhoff's voltage law, which says that, hey, if you have a supply and then parts in series connected end to end, that the voltages across the parts need to add up to the voltage across its supply. So that's an example of measurements that are taken. Resistance is also measured. And you have to customize your, so there's a ohm meter script, just like the voltmeter one we downloaded and used to measure. And it entails some modification of the circuit here. And the most important thing when measuring resistance is you have to take the thing that you're measuring out of the circuit in order to measure it. So measuring resistance does not work when you're in the circuit. After all those measurements, we start talking about measurement units, like the metric prefixes, kilo, mega, micro, milli, SI units, omega for ohm or resistance, hertz for frequency, and so on. So we introduce the units, talk about them, and we also go into making conversions. So if you see 1 kilo ohm, 1 K omega or 1 kilo ohm in a schematic, what is that number really? And after having introduced that so we introduced the metric prefixes here. And so here is, kilo is 1,000 and mega is 1,000,000 and so on. So they go through that. And then we say, okay, well, if you have kilo, you can replace that K with 1,000, and then you know what the number really is. Same with milli and seconds. And then we have also some chalkboard time with how to actually do that using algebra. And so that's done both by converting prefixes to values and also you want to go the other direction. We want to be able to say, okay, well, look, if we have, if we know the frequency is 38,000 repetitions per second, what is that in kilohertz? And so it shows how to get from, a number to a value that has a metric prefix and an SI unit. So those, and we make sure to introduce the algebra for that too. And so this is a place where there's some really good, basically intro to science material, and there's lots of good review and practice along with solutions and another copy. After that, we also measure current. So current is different from measuring voltage or resistance because you basically have to insert your ammeter. Well, first of all, we make a kind of a make your own ammeter by adding a very small resistor right there. And then taking the measurements, there's an ammeter script, and then you can take the measurements and see how much current is, electric current is flowing through your LED circuit. And it shows, hey, when we're measuring current, you have to actually insert the ammeter right into your circuit. And I somehow managed to skip that. Let's see here. Okay, so this was animated and I didn't realize that. Okay, so it's got you started with this. Here we go. See, this black wire was disconnected from the LED circuit. And then the ammeter is connected so that current flows through here, through the ammeter and back. Let's freeze that for a second. Okay. So right here, basically current is going to flow through the resistor, through the light emitting diode, and then into the red probe, through the small resistor, and then out the black probe, and then finally make its way to ground. So we have to disconnect the ground wire in this case. I mean, we could have put this anywhere in the circuit, but the idea is that you're putting the ammeter in series with the circuit. And that's an important distinction I wanted to mention if you're doing these lessons, that students will have to follow these instructions very carefully to add this resistor with these particular color code stripes, the 20 ohm resistor, and that they'll have to follow the instructions for disconnecting part of the circuit so that they can insert their measurement device right inside to measure the flow of current through the circuit. Okay. So that is just kind of a, oh, and then the last thing we talk about is Ohm's law in this chapter. And incidentally, I skipped over some of it, but there's always a script that's written to implement the math. So we introduce the math as in, here's how to do the math for it, but there always is a script that does something with Ohm's law. In this case, you're entering volts and you're entering the resistance of the resistor, and it tells you, okay, what's the current going to be given that circuit? And so, so this is one where you can say, okay, well, here's my Ohm's law solver for current. And then the students are challenged to solve for one of the other parts of Ohm's law. And Ohm's law, by the way, is voltage is equal to the current through the circuit multiplied by its resistance. Okay, I know that was kind of fast, but I just wanted to let you know it was there. Any questions or comments before we move on? Okay, I really wanted to make that available for any of you who did the original What's a Microcontroller with the basic stamp. You may have noticed that we more or less shied away from the math. But you know, since then, there's a lot more in terms of connect it and make it go examples. And I felt like there's a vacuum of actually taking it and applying the math and learning the units and things like that. So I went ahead and added that to this as something you can study as a student in this sequence of lessons. All right, back to taking measurements. Now we're going to measure with an oscilloscope. And I'm going to clean up and close a few tabs here. I'll leave the cyberscope open. Okay. So we currently have the voltmeter going, but there's another way to look at blinking on and off, and that is graphically. And so this is, get it right this time. Here is the web page I'm on for taking the, oopsie, I got a private text. Okay, let's try this again. Paste, there we go. And then I'll paste in a link to the hex file for you to download. So when you get to the, so you can right click and so when you get to the page, I think you can right click and select Save Link As, and then it'll appear on your downloads. Everybody got their file downloaded? Still working on it.
Andy, are we downloading 2 files or just one?
Just one.
And that's the LED blink with plot.
Yes.
Okay, because the other one just comes up with that same file from the other day with like the multimeter when we use that.
Okay.
That second link just opens up to a bunch of text.
Okay, yeah, so if you open the link, if you open it into a new tab, it'll look like that. But if you right click and select Save Link As, the link should be LED blink with plot .hex. And when you open that, by the way, go to your cyberscope tab if you have it open and hit disconnect. So we're gonna before loading code, we always want to have only one thing connected at a time. So we'll disconnect the cyberscope, then go to the python.microbit.org and drag LED blink with plot into the software. And flash it. Once you have the text loaded, you can go back. You'll want to disconnect your microbit, or pardon me, your Python editor. Go back to Cyberscope and hit connect. And when you do, it will basically show you little high and low signals as the light turns on and off. So I want to make sure everybody has gotten to this point.
Yeah, so I'm still struggling with that. When I use your second link or the last link you put in,
so
it's coming up as hex, and I can't download it.
Okay, yeah, that's my fault. It's not on my Google Drive. So when I sent you a link to a hex file that was on my Google Drive earlier, we were able to download it. And I made the mistake of pasting in a link to the hex file download from here. So what we want to do is I'm going to give you this page and then have you go to this page So there's a link to this page, and go to this page and right click this LED blink with plot.hex and select save link as, and hopefully it will appear down here in your downloads after you save it. Let me know if you can get to that point, Sarah.
Yeah, I think that worked. Thank you.
Oh, excellent. And then remember, okay, so after it downloads, then you'll want to drag it and drop it into your Python editor. Make sure you're connected, hit flash, then disconnect, then switch over to the Cyberscope and hit connect if it's not already connected. Okay, so are we ready to continue with this?
Andy, yours are really high peaks. Mine are really small. My guess is it's just a, the range, for the graph.
Yeah, I mean, for example, I just hit the 0.75 volt per division setting, and that brought it down. But if the size, what is the size of the high and lows relative to the numbers on the left? Are you seeing between 2.5 and 3 volts? We had a 2.7 volt high signal when we measured it with a voltmeter, and that's what we want to be seeing here.
I have just over 2. It's measuring around 213.
That's interesting. I wonder if you have a smaller value resistor. Check the resistor that's connected to your.
I have whatever we were supposed to put.
That's interesting. We'll want to take a closer look at that. But since you have a signal that's resembling this, let's keep going for now.
Okay. Yeah, I was just curious if because I noticed there are other things, and I thought maybe it was just a view setting.
Yeah, if it's down near 2, I think we're actually measuring something that's happening, and I'm not sure what it is.
Yeah, it's more or less a straight line.
Oh, so you have a straight line around 2. You're not seeing any of these highs and lows.
Correct.
Oh, okay. So what I would do is check your, now, did you get the 2.7 volt measurement when we were in our voltmeter?
I got the 2, when we did the voltmeter, I had the 2.71.
Okay. Okay. So, does it say disconnect in the upper left?
Correct.
Okay. So that means you're connected. But you have a flat line. It looks
More
maybe
or less,
something.
yes.
Yeah. So it maybe looks like that.
Yes.
Okay. So what I did to do this one might not be the same, but I disconnected from P13 and I plugged it into P14. So check your red probe and make sure that it's connected to P13, to the green light, to the resistor on its way to the green light.
Which?
That would be right here. So right here is the one that I had
okay. That's problem number 1. I took those off because I didn't think we were using them.
Oh, okay.
So no, sure. So P13, you say?
Yeah. So
right,
red goes P2 3-pin header to P13.
Yeah. All right.
And then black goes P0 header to right column with blue vertical line.
Got it.
All right. And so hopefully now you've got this or something like it coming up.
You bet I do.
Oh, awesome. All right.
Thank you.
So I like looking at this I don't remember what I did in the text. There is a very step-by-step to make sure everybody does this. I'm just kind of trying to hurry us all through it because 1.5 hours goes by so fast. And it's almost over. So I like to set the volts per division to 0.75. To me, that just looks more right because I've worked with an oscilloscope too much, maybe. And then some interesting things to try are to change your time per division. So like instead of 1,000 milliseconds for each of these squares, so see 1,000, 2,000, 3,000, let's change it to say 250 milliseconds per square. And then try 500. Now, do you see how it's kind of marching? That can sometimes make it difficult to view. So there's something called a trigger that you can start. And see the trigger menu on the bottom here? Go ahead and click the trigger menu drop down and set it to rise. And when you do, a little bluish and purple crosshair should appear. And then after about 10 seconds, if you're at 500 milliseconds per division, or 5 seconds if you're at 250 milliseconds per division, the rising line in the graph will line itself up with the intersection of those two crosshairs. And there's a slider to control the bottom crosshair that you can move. And when you do, the entire plot should move with it, albeit gradually. It always takes several seconds, typically takes several seconds, I should say, for the plot to update because it has to get, 5 seconds worth of points in the graph before it can actually update it. There's also a vertical setting, which doesn't really matter in this particular exercise. This is a way, of course, we're kind of skipping over the surface here, but this is also a way for students to change their code and learn about frequency and duty cycle and period. So they can actually measure the period. They can say, oh, well, my signal started at 500 milliseconds and then it repeated just after 1500 milliseconds. So that's 1 second. And so they can actually go through and do their calculations for period and frequency. And they can even change the script. So I'm going to make the light go on for a little bit less time than it's off. And so now we have a longer off time and a shorter on time. I think I want to accentuate that a little bit. Okay, so now you can see that there's a very short on time. The light only blips on and then it stays off for longer. And so that kind of loops us back to what we talked about in terms of frequency and duty cycle, which again is the ratio of the time the light is on, which is right here, to the total time before the light repeats its cycle. And those are all lessons that are in the main. Well, basically, if you go through it step by step, you're going to hit all of those little things. I'm basically just calling them out presently. Okay, so hopefully that was a little bit different and interesting. So your $20 microbit is now an oscilloscope. and a voltmeter and an ohm meter and a ammeter. And so that is now, I always in the original What's a Microcontroller, I wanted to include those parts, but that was going to make the kit too expensive. And so now with some software in a website, we have those features and we have the ability to not just say, oh, the light blinked, but to say, oh, wow, the light blinked. So what voltage was it applying when it was on? What voltage was it applying when it was off? What is the frequency? What is the period? What is the duty cycle of that on-off signal? We can see it with the light. We can measure it on the scope. We can measure, certain parts of it with the voltmeter. We can measure the current through the circuit. We can measure the resistance of a resistor in the circuit. So all those things kind of give the students hopefully a more complete picture of electronics and what it's like doing it. Real quickly before you go, I know we're a minute over at this point, homework for next time. So this is the what we have. We have our push buttons and our lights. And what I would like you to do is I would like you to add this servo. Oh, you know what? I just realized that there's going to be some steps involved in this. So I will send you particular pages. So there will be a page that shows how to add this servo. But the most important thing is please do not take apart anything you've already built. So I left it shaded in gray here because I want, I want us to be able to do some push button activities with the servo and with the potentiometer if time permits. So we're connecting a battery pack. Don't put the batteries in quite yet, though. I want us all to check our servo while we're here, as opposed to have you go through the tutorial step by step. Although you're more than welcome to do so. I'll show you where they live. Let's see here. So I'll just get myself to learn.parallax.com. So this is button presses, which will resume on Friday. Okay. So, nope. So here is the servo stuff. And the important thing is that it's going to show you how to connect and test your batteries. So yeah, the more I think about it, the more I want you guys to follow these tutorials. They're really short and sweet. So I'll send you this tutorial. It'll say, okay, you're going to connect the battery pack, put some batteries in, test the voltage. And you want to make sure it's about, 2 batteries end to end, which is about 3.1 volts if they're new. Then connecting the servo takes a few steps. The first thing you have to do is build this circuit right here. It involves a 3-pin header. And then after you've plugged in the resistor, the 2 wires, and the 3-pin header, then you can plug the servo onto the 3-pin header. So I was planning on just sending you this nice picture, but I just realized that there's a few extra steps. So I'll send you a couple of web pages so that you can put together the servo, and then just a picture for putting together this potentiometer circuit right here. And when you're done, it's going to look roughly like this. And then we'll do some stuff with the servo next time. Okay, so that concludes the informational portion of this presentation. I'd like to throw it open to discussion and question and answers. So the presentation is officially done, but you're all welcome to stay as long as you want to get your questions answered, especially.
Hey, Andy.
Yes.
This is Brian. I just wanted to mention those 2 batteries that came from some country somewhere that came with the kit. They lasted me about 2 hours on Sunday and they died.
Oh,
so
no.
You might want to have backups ready.
Okay. Thanks for mentioning that. I'll add to the homework that I email out. Oh, heck, I just remembered that there's one more thing for all of you to be ready for, and that is that there's going to be an email from Parallax. If you don't already have teacher access to learn.parallax.com, we are going to give you access and you'll receive an email from us, and make sure to set yourself up with that. If you receive the email. If you don't receive the email, the instructions in the homework are going to say, go to this address right here and sign in to learn.parallax.com and use the request new password if you forgot your password since whenever you signed up for it. And that will allow us, that will give you access to the teacher materials that I've mentioned, and you'll want to have that for when I start showing those materials to you on Friday. Oh, here, did you need to get a screenshot of that? Okay. Okay. Boy, I hope everybody else sees that in the email. We'll see. So what do you think of that? I kind of like it. I kind of think that there's some more actual meat in addition to just building the circuit and seeing it happen. There's things like the breadboard. Well, in most textbooks and web pages, it's just a picture. But here we had, little images of, hey, two wires went into the same row of 5, they were connected. Hey, two wires went into a different row of 5, they were not connected. Things like that are things I'm trying to add into this to make sure that that students to remove as much mystery as possible from the electrical and electronic lessons. And so I'll be looking forward to any emails saying, hey, Andy, there's still a point here where my students are really scratching their heads. We had this idea that if you added this diagram, that it would help. So I'm really interested in any feedback you might have that's like that. Yes, Rich, go ahead and unmute. Nope, can't hear you yet. There you are.
Okay, I'm using the space bar for unmute, and sometimes it just doesn't work. I don't know why. So, so I think this is all really, really good. And so one thing that I've done in the past with the propeller and with basic stamp is after connecting the LED up to the positive bus just to turn the light on, I'll have the kids tap it, on, off, on, off, on, off, and have them go faster and faster and faster. And then when we
go, okay,
yeah, then
I
when
like
we go,
that.
yeah, and then when they go to say, all right, let's make the microcontroller do it, and then they can see why we can use electronics to make things easier for humans. Things that have to act very quickly, flash quickly, or control stoplights or something. And I ask them to imagine like somebody inside the yellow box on a pole at an intersection, tapping to the wires to turn the red, green, and lights on and off, that kind of thing. We can use microcontrollers for that. So anyway, I think this is really good. And I was wondering if you could give us a suggestion on marketing this to a school. I'm looking. I wanted to start a programming class.
Okay.
But I think just a plain programming class, to me, it's just kind of boring. If we add the electronics part to it, then it becomes hands-on, and they're making programs do something, communicate
Yes.
with people, communicate with the world, and so forth, and it's interactive. So then it seems inappropriate to call it a programming class. But I don't want to call it electrical engineering because that's kind of scary to some people. And
yeah, well, that's why they came up with the word STEM, was to
yeah,
kind
right.
of declaw it a little bit.
Right. But that's become so diluted now that
Yeah. STEM is often
yeah,
associated with just a whole bunch of gee whiz. It's true, and there's
yeah.
that, and that's not to say that there aren't some good things in STEM education offerings. It's
Right.
just that there is quite a lot of connected. It worked. Let's do something
Yeah.
next.
Right. And so, it'd be good to add in, the science. You mentioned, for example, metric prefixes. We have graphing going on here. And so I'm thinking like, something that suggests to parents and to students and to other teachers in the school that we're talking about something here that's very inclusive and it's very, it can be tightly integrated with classes that are taught conventionally in the school.
Yeah, so programming and real world applications, maybe.
Yes, or
Um,
something. Yeah, something on that path. Yeah.
yeah, I do see that we'll want to add a name. Now, one other thing that here's a thought that came to mind. Basically, if we go to makecode.microbit.org, so this is the block programming. Thing is, actually, I'll do make it coded as well. See, new tab, make it coded. Oh, that's, let's see here, microbit. There's make it coded. Okay, and I need to put these guys in the chat for you. Here you go. Okay, so one thing is that the microbit, in a way, is a microcosm of a cell phone. So we're looking here. We have buttons. We have a digital display. We have the ability to shake the microbit and have it recognize that it was shaken for things like digital dice, magic 8-ball, step counter. Then we've got music. We've got music with the simple circuits that you can do with a microbit just on its own. Temperature measurement, compass bearing, all kinds of things that are real world programming applications that go into a cell phone. So that's one way to add to it. And by the way, there are lessons that go with this, and some of it's a full curriculum. Let's see here. There should be a computer science one. Computing fundamentals. So here's the lesson summary and the curriculum links. These are things you can do before you ever start with the circuits. And so this is the whole curriculum bundle. And there's a similar one down in make code. So make code, yeah, sure. It takes you step by step through, say, block programming and Microsoft's version of Python, which is very different from the BBC's version of Python. The BBC is the creator of the microbit. But this walks you through how to create the program, and it says, all right, go and click the basic and select show LEDs and put it in the forever loop. And then you keep on going through and following the instructions, and that's well and good. But what I wanted to get to here was that once you've got your code going, there's a simulator, and you can look at it in JavaScript or in Microsoft's version of Python, which again is different from the Python that we've been using. The syntax is somewhat different. And so I'm never sure really how much to talk about this, but it is another Python resource, and it is basically Python. It's just so different from MicroPython that is presented with the other editor that we've been using. But anyway, so I kind of got off track because what I really wanted to show you here was that there's also curriculum that's microbit centric that can come before an electronics kit, so that the electronics kit can be so that it can be, you can split it up into modules where different things are introduced. And I'm sorry for scrolling so much here. Courses, here we go. So here's the Intro to Computer Science course. And it's set up for 14 weeks. And there is a full bundle. I actually want to go back, because there's the online Intro to Computer Science if you're taking the class, but there's also the classroom version where you can download the entire curriculum, and it's like a gigabyte, 1.4 gigabytes or something like that. Here's the complete course package, and it takes several minutes for it to, oh, well, I lied. Now it's downloading a 1 gigabyte zip, which I don't want to do at this moment. But so there's a lot of material that you can do with the microbit that is, programming as in computer science, before moving on to programming in the context of building circuits. So there's the final answer to the question. Sorry, that was a little bit roundabout, but I figured it would be that there was some useful information along the way.
Yeah, I'm wondering if naming it something like programming to interact with the world or something like that might be catchy and really reflect what we want to do.
Yeah.
And because we're talking about push buttons and lights, so it's interfaces with humans and with machines and so forth.
Yeah, I feel like there's going to be a really good name, but that it's not going to occur to me until, say, tomorrow morning. So let's all stick on that. I'm sorry, what's that, Stephanie?
Programming for gadgets.
Oh, I like that, actually.
Oh, yeah.
Programming for gadgets.
Yeah.
Okay. We'll add that one to the list, and then, let's all percolate on that one and see if we can come up with a good name for it.
Well, thank you.
Oh, certainly. Yeah, absolutely. All right, then. So anything else?
Andy, I wanted to thank you for bringing the oscilloscope in, because in all the years of teaching micro, I never thought of pulling a scope in. So I pulled my scope in.
Ah, looking good.
There it is. Just happen to have one right there.
Yeah, mine's a little bit too heavy to actually lift up. And truly my pleasure, because one of the things that I noticed early on was when we did these classes for What's a Microcontroller, if the place we did the class ended up being an electronics lab, invariably we'd turn on, we'd connect the voltmeter, we'd look at it on a oscilloscope, and there'd be further learning. But in terms of in the classroom, I couldn't guarantee that everybody would have access to that. And now everybody can have access to that. So that's definitely, I'm glad to finally be here 20 years later. All right, then. So is there anything else, or let's see, I'd better stop recording while I'm at it here. Okay. So stop recording. Are you sure you want to